Hello, my name is Timothy Hydonis. And today I'm going to be presenting on AES encryption, a little bit of quantum computing, and the future of encryption in light of quantum computing itself. Now, just to give you a little bit of an idea, encryption is used in every single part of computing at this point. Anytime you send a text message, use your email, or just browse the internet or log into a website like Facebook, you are using encryption at some level. And as we're going through our degrees, not a lot has gone into necessarily explaining how an encryption works. We just kind of know it jumbles up the data and makes it unreadable, and we have a magic black box that jumbles it and unjumbles it, and that's kind of it. What I want to do today is kind of crack open that magic black box, give us an idea, just even at a very overview style, of how it works and what it does, and give you an idea of what the future of that's going to look like. Now, to give you an understanding, this one here, AES encryption and cryptology, is an entire field of study people spend their entire lives mastering, and quantum computing, another field that people spend their entire lives mastering. I'm going to boil it down to 15 minutes, so please bear with me. So just as a start, I'm going to go into what cryptology is, what the AES standard is, how it works, quantum computing, and then I'm going to kind of summarize it all together. So diving right in, just a few concepts, some terminology to know about cryptology in general. It breaks into two primary fields. The first is cryptography. Cryptography is the study and analyzation of algorithms, how we can improve them, how we can implement them and such. And cryptanalysis is looking at an algorithm saying, well, how secure is this? How good is it? Can we actually get into it? And can we read the data that's being hidden? This over here is an excellent example of what the average algorithm that we're going to be using is going to look like. You read in what's known as cipher data or ciphertext, plain text. I'm sorry, not cipher data. You read in plain text data, which is unencrypted. It is what you want to be hiding. You pass it into this magic black box, the encryption algorithm, and you compare it against a key. You pass that in as well, and you get out ciphertext or cipher data. This is encrypted and is supposed to be secure from anybody who's not supposed to be able to read the information. Now, just to diving into a very simple example of what an encryption is, I'm going to go over Caesar shift. Now, Caesar shift was invented by a guy named Caesar. Go figure. It was the Roman emperor. Don't worry. And the way he came up with encrypting messages that he sent was he said, well, what if I just take the alphabet and I shift it over by a little bit so that if I wanted to put the letter A in, this was what I originally had, I would put the letter Z instead into my letter. Or B, I would replace with A, and so on and so on. And that was really, really good. People looked at it and said, well, this is a bunch of garbled information. We don't know how to read this. But once people figured out how his algorithm worked, there was a problem. There's a limited number of combinations you can have of this specific algorithm, as long as you're keeping the alphabet in order. Because our current alphabet has 26 letters. You can only shift over 25 times until you're suddenly saying, well, A equals A, and B equals B, and that's not really secure. And as you go over 27, well, you may as well just shift by one at that point. So there's only 25 possible combinations of algorithms that you can create with this. So suddenly, well, why do we have to keep it in order? Let's scramble it. It's called a substitution cipher. So now A is D and B is, where is it going to actually? It's going to G. And it's a lot more complex. And it actually opens up the possibility in what we call complexity in algorithms. Or not, in algorithms and also in cryptography. Is now instead of having 25 possible combinations, we have 25 factorial. That is the number of combinations that you can have, which is 15 septillion possible algorithms, give or take a few. Which is a couple millions times a million, roughly speaking, just to give you an idea. It's very, very large. So the odds of someone just looking at what you have outputted into your cipher data and just going, well, I think this is the algorithm that they used, and trying to guess it specifically, the combination they used, is nearly impossible. Even for modern computing today, if you just tried to brute force this algorithm right here, it would take you several years. So what we have to do is we have to look at it and we have to do a targeted analysis. One way that this will be beat is through letter frequency analysis. So we look for the most common letter of the alphabet, the letter E. Then we can also look for like three-letter words in the output. So you can look for T-H-E and look for three-letter words that end in E. Well, hey, look at that. That's probably the letter the, and you've already found 3 letters out of the alphabet. So through analysis, thus cryptanalysis, that is that field of study, we can actually look into how to defeat algorithms. And the key to making everything hard to beat for someone who's in cryptography is you have to look at it and make it so complex that you can't analyze it and you can't guess it. And even here, though, we have another problem that Caesar had. As soon as the algorithm, and we know what the algorithm is, we know this specific thing, this is how it works, if someone knows that, they know every piece of information you've ever encrypted with it. So what about that diagram I showed you originally? This one right here. There's no key we're passing into a substitution cipher or a Caesar shift, and it gets down to a concept. Well, that is the wrong direction. There's a concept called Kirchhoff's principle. Now, he was a guy that lived in France about the time of the Revolutionary War, and he came up with this idea here, which is you assume that the encryption and decryption algorithms are known to your adversary. The only secret is the key. In other words, I could encrypt something, and I could hand you the algorithm, and I could hand you the output of my algorithm, and as long as I hold on to that key, it should be secure. Now, the NSA actually took that to heart when they were creating the current standard for encryption called AES, or Advanced Encryption Standard. They were phasing out an old encryption standard called DoD, which I don't remember actually what the algorithm for that stands for. But they were saying, it's not secure, we need a new one. And so they went to the entire world and said, we need a new encryption algorithm. And the entire world responded with about 15 possible combinations, including big names such as IBM, the creators of Watson. And what the NSA did is they said, we're going to give you some data, individual data for each submission. And they said, we want you to encrypt this with a key. Hold on to the key. Your algorithm and your output is going to be released to the entire world for the next 4 years. And the last man standing will become the AES standard. After about 4 years, there were 4 algorithms still standing that had not been cracked and that were still secure. And of those, the most efficient one, which was known as Rheindal by 2 guys from Denmark and Iceland, I believe it was one from each, they created the algorithm that was the most secure. They somehow beat out IBM. I'm not certain how that happened. But this is roughly an idea of what AES does. Now, there's a lot of things going on here in this diagram here. But suffice to say, everything below here is reorganizing the data so that it can be reread in a simple way without leaving any distinguishable patterns to a cryptanalysis expert. The main part of the encryption is actually similar to the substitution cipher, where we read in information and we read out a random, or what seems to be a random output for what was read in, which is actually this step right here, called S-box substitution, or as it's often, byte substitution, or what is called S-box encryption. What is done is based on the size of the key that you have, which is down here. You would read in double the size of the key. So if you had a 128-bit key, or 128-bit key, you read in 516 bits. Then you'd break that down into 4-bit increments and pass each 4-bit segment into the S-box. Then it's broken into 2 segments, so 2 bits each, and read as individual numbers. Those correspond as a row and a column in a table lookup. So you read in 4 bits into an S-box, and you read out 2 bits. Well, that's kind of confusing because now we are going to be losing data out of the algorithm. Well, not quite, because you're actually cutting down the data in half. Then, as you get down to here, you compare. Keep in mind, we read in twice as many bits as the size of the key. So we've cut it down in half, and we're passing down here. We get to this key, which is compared to the outputted data that's been encrypted using an XOR gate. So then you have something that's really encrypted. It's been passed through a key, but we're still got half of the data. Well, what we do is similar to what Casey was talking about with his blockchain. Was he was saying, well, we can pass in information, we get a single size encryption. Well, you can actually, or a hash. Well, what you do is you take a hash of the data that you passed in. Well, reverse engineering a hash is very, very difficult and nigh impossible. So what you do is you actually take the encrypted data, take the hash, and you put them together. You have the original size of the data in the same amount of space, but it's really, really hard to read. Now, this in of itself is called a round, and if you did this once, it seems pretty secure. Now do that 10 more times. That's AES. It's very, very secure, and the NSA uses it as their industry standard for top secret information. It is used at all levels, and to this date, there's no publicly known way to defeat it, though many people have, are, and probably will continue to try. Now, to get into this though, we have to understand that as we move through encryptions, we can't assume that the one we have is secure. The Mary the Queen of Scots, we've all heard that story of her. She was trying to overthrow her sister, and she was passing messages along to conspirators and such. Well, she used an encryption, which was substitution cipher. And as I mentioned, there is a way to defeat it using letter frequency analysis. She assumed that that algorithm was secure. It had been for the past 2,000 years, so why not now? And someone read it. Someone passed it along. And suddenly she got her head chopped off for it. So we probably should be careful about assuming that our algorithms are secure. We have to continue to look forward to what is next in encryption and in algorithms as a whole. One of the main factors in encryption is Moore's law. As time goes on, every year and a half, the number of microcomponents, or transistors usually, is doubling in most computers. Except we're progressing towards a breaking point in Moore's law, because there's a lower limit to how small we can go as a component in a computer, and that is the size of an atom. By the year 2020, transistors will be so small that we will have to resort to using reading and writing data from an atom. And this is what is called quantum computing. Now, I'm very sorry I don't have any diagrams that really clearly explain what quantum computing is. There's a problem with that because we don't actually truly know what an atom looks like. We just know it is. We can't view it, and nothing about an atom actually follows Newtonian physics. So how do we view it? It's very, very hard. Even Einstein looked at quantum computing, threw his hands in the air and says, it's a given. We have to accept that it happens because we do something and we get a result and we can measure that, and that itself is science, but we can't understand why. He basically said, we can't. Edison, the guy who knows pretty much everything. So I'm very sorry. But what we have when we get down to an atomic level is called a qubit, or quantum bit. Now, it has a very unique ability. A quantum bit, well, you read and write data from it. Now, no, we do that all the time. You know, you you write into a transistor, you write a 1 or you write a 0, and okay, well, what's new? Well, you see, a qubit has a unique ability. It has a superposition. It could be a 1 or a 0 and a 1, or a 1 and a 0. It's actually got 2 bits inside of it, which is very, very powerful because instead of having a single bit that is capable of handling 2 numbers, you actually are capable of handling much, much more. In fact, it is 2 to the n processing power out of a qubit. And perhaps I should mention this. Instead of thinking of it as reading and storing data, a qubit is in of itself a processor. And if you team these together, you have a lot of power. So if you have 500 qubits, you actually are capable of performing 2 to the 500th power operations, which for a scale of the number of processes that's more atoms than there are in the known universe. So that's a lot of processing power. You start tying these together, suddenly AES isn't as secure as we were hoping. Now we can add to the complexity, we can try and make things more secure, but if there's an analytical process for defeating it, we have to find something better. And currently, we don't actually know what that is. It's a study called post-quantum computing, or post-quantum encryption. And the NSA is already calling for new encryptions as we go through time, as we progress towards that breaking point, which is estimated to be about 2020. We're expected to need quantum computing to go any smaller. And it's very complex. It's very hard to go into because there's no defined way to go into post-quantum computing. It's all very theoretical. It's all very experimental. And it's expected it's going to take about 20 years to implement any new encryption. So we have to start now, even though we don't have quantum computing on a large scale yet. But hopefully what I've given you is just an idea of what encryption does, how it works, and a little bit of what we should be looking forward to in computing and encryption in general. Thank you. So, I know there's a lot of questions here. Go for it.
Have you done any research on possible quantum security? Because I know that you talked about it not being secure anymore, which is not.
Yeah.
So what are the alternatives?
One of the biggest ones that I looked into just recently is called lattice-based cryptography. Now, if any of you are familiar with the traveling salesman problem of going from, you have a bunch of cities, you have to get to the shortest path amongst them, the number of possible combinations you could have for traveling between city to city is theoretically infinite. You could do any number of them, you could pass through any number of them as many times as you want. It is actually possible to have an infinite number of combinations with a finite points. There are some studies being done into using that concept, using lattice-based cryptography towards encryption, where you have, rather than having a finite set, like with the substitution cipher that I mentioned, there's 15 septillion combinations. We can count how many possible combinations there are, which means with the amount of processing power quantum computing has, you could theoretically calculate it over time. With a lattice-based cryptography, there is an infinite number of possible algorithms. So you would have to brute force until you find an answer, but you don't even have a defined point where you know you have to find an answer. So it's a lot more secure, but it's very theoretical. Peter?
Do you think that, obviously once computer comes out, modern encryption will be absolutely pointless to have. What do you think the realistic probability of having to need quantum grade encryption are, being that the primary reason why we have encryption on a daily basis is for your average Joe hacker.
Yep.
However, your average Joe hacker won't have a quantum computer for at least, it's going to be at least 50 years before there's even access to your average Joe. So do you think that there's going to be kind of, the race might not be as urgent, or do you think?
I would like to think that it's going to be not as urgent, but also the NSA is calling for it because they have to protect national security as well, because just because the average user doesn't have access to it doesn't mean China won't have access to it or Russia won't have access to it. I mean, not to go to that trope, but at the same sense, we do have to make certain that we are secure. The difficulty is that I would expect we would probably have it at a business level first and also at a government level to an extent, but the application isn't going to be so large that we can have, 500 qubits or...
That makes sense, and then effectively, the business side of it could take control of the government side of it, either not only overthrow it, or just maybe just even turn it in their favor.
Yes,
which is bad.
And the other difficulty with developing any algorithms currently for quantum computing is the processing power required to handle an algorithm that would be resistant to quantum computing kind of requires an equivalent processing power to quantum computing, which we don't have yet. So we need the quantum computer to make post-quantum encryption, but we don't have... Yeah, it's this really complicated thing, and I agree with you. It's going to be a phase where it kind of slowly trickles in. It might not be that big of a concern, but if we don't start considering it now, it is something that will be a problem in the future.
It'll be on our doorstep before we know it.
Yes.
Okay.
If you can use quantum computing to brute force decryption, can't you use quantum computing to encrypt?
Yes, that's one of the factors. But most of the algorithms that we have right now are not efficient enough for classical computing, because if you have a 64-bit processor, you can only handle a bandwidth of 64 bits. Whereas a quantum computer, wasn't able to really go into this, but you can do more than just say perform this operation. You can say perform this operation and iterate back and go through a massive field. In fact, quantum computing, depending on how you read and write information from that qubit, you can natively perform operations such as the modulus function that would normally be a recursive call that you can do with one, maybe two passes without any difficulty at all. So it's kind of one of those balances. It's very efficient. It's also not fast necessarily. It won't replace what we have, but it will certainly become a very powerful companion.
So you mentioned a lot of encryption about like kind of high-level encryption. We don't really encounter that very much. What would be a good example of encryption that we encounter every single day as just regular?
That's a good question. Anytime you see in your URL bar HTTPS, it's using a protocol called SSL, which uses a version of AES as a security as you're going through. Another example would be if you use FileVault on a Mac, that actually if you choose the correct options, it will encrypt your hard drive, and that's using, I think by default, 256-bit AES. No, I'm sorry, 128-bit by default, and you can customize it even further. I think I can on this Mac if I wanted to go up as far as 512, I think if I wanted to, or 516, I think it would be, because it's double. So you can use it on a daily basis. I encrypt my computer personally just so that as a business-minded thing, it's not really because I am trying to keep something top secret. It's really not that pertinent for me. But for going into my field, I'm going to be working to try and secure my company's data. And so it's something that I should be mindful of. And we do use it on a daily basis. It's just at such a level that we don't notice it, and it's being implemented almost smoothly. Like, you have an iPhone there, right? That's encrypted. Apple is doing that right now. Ever since the scandal with the NSA saying, oh yeah, we're spying on people, Apple's upped their security. They started encrypting their devices. They started going everything very, very secure. And we all probably remember the San Bernardino shooter with the phone that the FBI couldn't get into because Apple wouldn't violate their own security and the privacy of their users. So it's being used very often and being implemented more and more. I think I saw a study that said there's been about a 50% increase in the use of encryptions over the past 2 years, and it's expected to spike even more.
Talking about like the San Bernardino issue and encryption as a whole,
Mhm.
where do you think that? I mean, this could be a total question that's just opinionated, but
Yeah.
where do you think that should lie? Do you think it should lie in the control of like the individual consumer, where they have the right to everything on their phone, or do you think that in an instance like that shooter, Apple should be able to violate that thing? I mean, like, because you're talking about obviously quantum computing ruining the ability to encryption as a whole, right? So,
As we know it, but we're expecting to have things that can handle it. Yes.
Yeah. So I mean, but it's the idea that your data should be private. If you want it to be private, right? So
Yep.
you're talking about the ability to use those tools. Where do you lie on something like that?
Personally, I don't think it has to be forced on everyone. I think it's good practice.
Mhm.
But as far as the privacy of data, that should be the end user should have the option, at least if they wanted to opt out of it. But I think you should never limit the capabilities of what a user can do with their computer, because the more you try and limit something, I think the more people will want to try to do it themselves, with whether you want them to or not, which might even ultimately make it harder. Where if you have a publicly available tool that everyone knows is relatively secure, but if you absolutely positively had to, with like quantum computing, you had to get into it if you put a lot of resources into it. I mean, that's probably better than someone going, the tinfoil hat wearing kid going, hey, I have a super phone that can't be beat by the NSA at all. I think it all should be up to who's using the information and how they want to secure their own data.
Yeah.
And it should never be you can't. I don't think it should ever go that far.
So AES encryption is, AES encryption is symmetric key encryption.
Yes.
Where you both have the same algorithm and key.
Mm-hmm.
When you start talking about things like the RSA algorithm, which is asymmetric key encryption, public-private key encryption.
Yeah.
Because of the way that you do, that encryption using like modulus functions and whatnot.
Yeah.
It theoretically is actually impossible to brute force like a public key encryption algorithm. Is that
Theoretically, yes.
Is that correct or is that not correct?
For current capabilities, that is correct. But for RSA keys through prime number factorization, which requires the modulus function, which is why it's nearly impossible with classical computing, and I would argue same way that it is impossible with current computing capabilities. I mean, there comes a point where if you have the capability to run as many processes as there are atoms in the universe in a single pass, yeah, you could just guess the RSA key at that point. But by adding complexity, you can just try and stay a step ahead of that. I mean, it's kind of all a toss-up in the air of how people react to quantum computing. Like, I don't know if that really answers your question, or...
Well, yeah. I mean, I guess with the mod function, you get a number that you can't work backwards from.
That's the idea.
Because you can't work backwards because it could be any of a set of numbers.
Mm-hmm.
So you could theoretically check every single number that fits in that set. You could work it backwards.
Yeah.
And check every number that, gives you mod, that gives you a remainder of 17 or something. And you could actually work backwards and check every single one of those. But with the 256 byte or 2048 bit key, which is what RSA is using.
Yeah.
With, like you said, with current computing, it's not possible. It's
Mhm.
not actually possible within anyone's lifetime.
Yeah.
To brute force that. But with quantum computing, you're saying that you could process so much data at
Mhm.
once that you could actually check every number in every
Mhm.
set.
For modern encryption, yeah. There's some people saying that encryption in general is dead because of quantum computing. I don't think so. I would say that there's going to be a point where probably there will be a point where it's like, yeah, our information isn't quite as secure right now until encryption catches up. We've kind of actually been very fortunate that that cryptography has been very far ahead of cryptanalysis for years and decades. Basically, ever since World War II when computers came out, we were very, very far ahead of algorithms, but there was a long time prior to World War II, before we actually came up with the idea of using machines in encryption, that there was actually no way to safely secure your information through cryptography. And it was literally the only way was to keep your information safe was don't show it to anyone. And so that's going to probably get to a point where that's where security is going to have to be for a few years until post-quantum encryption catches up. But I do think that there's enough work and brain power being put into it that it's not at all feasible that we'll then catch up to quantum computing very quickly and get it one step ahead of it. I mean, naturally, complexity, because you said like 256-bit key, but what if you went up to 128-bit key? I'm sorry, not 120-bit, but you go with a 1,000-bit key or a 2,000-bit key. There comes a point where that sheer complexity will still overwhelm a quantum computer. It's efficient, but not that efficient.
You had a chance to explore this chosen topic. Do you see yourself wanting to do any of those along those lines after you do this place?
Most likely not. I actually went into it just because it kind of was one of those things. I think I actually had this conversation with you, Jason, was, well, it's an encryption. Well, how does it work? Well, it encrypts things, and how does it encrypt it? Well, it runs it through an encryption algorithm. And it was just kind of like, it was in networking, I think. But it was like kind of like I just wanted to know more about it so that I could at some level understand it and explain it to someone, which I feel at this point I've done. If I went much farther, I'd be going into cryptanalysis and figuring out how to break encryptions, and you start experimenting with how to defeat the security functions for all of the top secret information over at the NSA, and you wind up on a few watch lists, as I understand it. I personally would like to avoid that.
Close the way under the cover.
Yeah.
Although the
I-
title of your talk, which is being streamed on Facebook, even as we speak, is probably only put you on the list.
Just go to about they can't track you, right?
Besides that,
Wow.
they avoided detected the phrase NSA and encryption in this talk. So.
Yeah, let me just say I'm sorry. But no, I kind of took on this project as an academic endeavor of just understanding it and being able to explain it, so that if I was working in the business field and someone said, well, how do we secure just our local copy of things, and I could say encryption, they go, well, what is that? I have a deep enough understanding that I could sit down and say, you know what, here's a 15-minute discussion of what actually this is so that you know that your information is secure. So it was more of a utilitarian of just a knowledge base, not necessarily looking into going into this field.